Hello everyone. We will start and begin shortly. Please try these review problems as we are waiting for people to join. Hello everyone. So please try the review problems. We will begin in a minute or two. The raffle winners will be announced so shortly. Okay, now let's begin with let's start off by going over the review problems. Okay, so now let's begin with the first review problem. Okay, so in this first review problem here, we have that find the sum for all values of k for which the polynomials x squared minus 3x plus 2 and x squared minus 5x plus k have a root in common. Okay, so how can we find out what this is? Well, as you can see here, the roots of x squared minus 3x plus 2 we can factor this into x minus 2 times x minus 1 equal to 0, which means the two roots are 1, 2, the two roots. Okay, so the two roots are 1 and 2 of this quadratic. What are the roots of x squared minus 5x plus k? Okay, so as you can see here, x squared minus 5x plus k, well, if it has a root in common, we have the two cases. Either the root 1 can be in common, or the root of 2 can be in common. But as you can see here, the two roots of this quadratic are going to be r and s. So r plus s equal to 5. And we also have the r times s is equal to k. So if r plus s is equal to 5, and we know one of the roots that is in common is either 1 or 2, then we know that they can either be 1 and 4, so 1 plus 4 equal to 5, or it can be 2 plus 3 equal to 5. So that means the two possibilities for both the roots are 1 and 4, and 2 and 3. That's great. Okay, so now what? Now that we know that the two roots can either be 1 and 4, 2 and 3, now what we can do is we can just find the product of the roots in both of these cases. So in the first case, the product of the roots will just be 1 times 4, or 4. In the second case, the product of the roots will be 2 times 3, or 6. So the sum of the values of k, or the sum of the values of the product of the roots, is just going to be 4 plus 6, which is 10. And that's the answer for this first problem, review problem here. Okay, so now let's move on to the next problem. So in this next problem here, what we're going to do is we're going to expand the whole thing out. So let's just expand it so we can get x squared minus a plus b times x plus ab. And then we also have x squared minus b plus cx plus bc. And when we add them together, we get 2x squared minus a plus 2b plus cx plus ab plus bc. Okay, so now what can we do? Well, we have this new quadratic here, and we want to maximize the sum of the roots. What will be the sum of the roots of this quadratic? The sum of the roots of this quadratic is just going to be equal to a plus 2b plus c divided by 2 by Vieta's formulas, which is equal to, well, we want to maximize this quantity. And we know a, b, and c are 3-digit one-distinct numbers. They're 3 distinct one-digit numbers. So then if you want to maximize this quantity, we can just say that b is 9, a, that's not it. We can just say b is 9, and a is, let me just use a different color just to make it clear. So let's just plug in a equal to 8, b equal to 9, and c equal to 7. Because when we plug in b equal to 9, we want to maximize this quantity right here. So if we want to maximize the value of a plus 2b plus c, what you can do is you can just see that the maximum value of this quantity will just be maximized when b is maximized first. And also a and c have to be maximized. But since we're taking 2 times b, we want to maximize b, make b as big as possible, and then we also want to make a and c as big as possible. Okay, so overall the sum is 18 plus 7 over 2, which is 33 divided by 2, or 16.5. Okay, so now let's take a look at our next problem, our next topic, which is going to be some algebraic manipulations and factorizations. That's today's topic. Okay, so some basic exponent rules are that x to the power of negative a is 1 divided by x to the a. So for example, x to the negative 3 is equal to 1 divided by x to the 3. We also have that x to the a times x to the b is equal to x to the a plus b. So whenever you're multiplying x to the a and x to the b, it's equal to the x to the power of the sum of a and b. And then when you do x to the a divided by x to the b, we have x to the a minus b. And then we also have x to the a to the power of b is x to the a times b. So basically when you're dividing exponents, we subtract the powers. When we're multiplying them, we add the powers. And when you're changing to the power of, we multiply the powers. Some factorizations here. So x squared minus y squared is equal to x minus y times x plus y. X plus y squared is equal to x squared plus 2x plus y squared, which is equal to x minus y squared plus 4xy. So basically, this is something that you should definitely memorize. And this is also something you should memorize for sure. And this is just an alternate way of, kind of phrasing it. So this is just an alternate way of rewriting x plus y squared. Because you can think about x plus y squared as x minus y squared plus 4xy. But you don't need to memorize this. You should just be aware that it exists, because in some problems, you might want to relate x plus y squared and x minus y squared. So it's always a good thing to know. We also have that x minus y squared is going to be equal to x squared minus 2xy plus y squared, which is equal to x plus y squared minus 4xy. And again, this is something that you should definitely memorize. And this is just, the next one is just another way of rewriting x minus y squared. And then we also have that x plus y squared times plus x minus y squared is just 2 times x squared plus y squared. Okay, so the reasoning here is that the 2xy terms will cancel when we add them together. And then also when you subtract them, you get 4xy. And again, the things that I pointed an arrow to, those are the things that you should definitely know. And the other ones, you don't need to memorize them. They're just good to know that they exist, because in some problems, you may want to use these different ways of expressing certain expressions. So that's why it can be useful at times. Okay, now let's take a look at our next factorization here, which is that x plus y plus z squared is x squared plus y squared plus z squared plus 2 times xy plus yz plus xz. So basically, whenever you have x plus y plus z squared, you can rewrite it in terms of x squared plus y squared plus z squared plus 2 times xy plus yz plus xz. So this is another factorization that has come up before, so it's definitely good to know. Now let's take a look at Simon's favorite factoring trick. So basically, you have this long expression. We have this equal to the sum of these terms. And don't worry if you don't understand it now. We'll go into many more examples that will hopefully make it a lot more clear. Also, we have something called Sophie Germain's identity, which says that x to the 4 plus 4 times y to the 4 is equal to x squared minus 2xy plus 2y squared is equal times x squared plus 2xy plus 2y squared. So this is an identity that it might seem really strange at first, but it has come up many times before. So it's definitely a good thing to know. And basically the reason this is true is because we can use different squares, and I'll show the proof quickly now. Also, this is actually known to make some really hard AMC and AME problems really easy. So this is definitely something that has made hard problems really simple. So it's definitely something that's really powerful. And the reason it's true is because we can express it as x squared plus 2y squared minus 2xy times x squared plus 2y squared plus 2xy. And this is just difference of squares, is equal to x squared plus 2y squared minus 2xy squared. And this, I'm not going to show the whole algebra here, but if you expand it and simplify it, we get x to the 4 plus 4 times y to the 4. And this is just a clever application of difference of squares, and that's how we actually get to prove this identity. Okay, so now we're going to start off with some simple AMC 10-12 problems. And then after that, we're going to work our way to some harder AMC and AME problems at the end. So let's first start with some simple, easy AMC 10-12 problems. For what value of x does 10 to the x times 100 to the 2x equal to 1000 to the 5? So how can we do this? Well, we can rewrite everything in terms of powers of 10. So we can rewrite it in terms of powers of 10 to get 10 to the power of x times 10 to the power of 10 to the squared to the power of 2x equal to 1000 to the power of 5, which is 10 cubed to the power of 5. And then we can rewrite this, and we can get 10 to the x times, and remember, when you're taking an exponent to the power of another exponent, we multiply the exponent, so 10 to the 4x equal to 10 to the 3 times 5, because we're using 3 times 5, so 15. And then we can make this into 10 to the power of x plus 4x by the exponent product rule, so 10 to the power of 5x is 10 to the 15. This means that 5x is 15. Or x equals 3. So now let's move on to another easy problem from the AMC 10. Assuming a is not equal to 3, b is not 4, and c is not 5, what is the value of this expression? Okay, so this expression, how can we find out the value of it? Well, firstly, the only reason that they said these a not equal to 3, b not equal to 4, c not equal to 5 is because if a was 3 or b was 4 or c was 5, then the denominator would be 0. And that's not good because that would mean the expression is undefined. So that's why they mentioned that, just a small workaround there. They just wanted to make it clear that you're not dividing by 0 here. And now what we can do is, to solve this, is we can rewrite it so that's a minus 3 divided by 3 minus a. And then we also have b minus 4 divided by 4 minus b. And then we also have c minus 5 divided by 5 minus c. So then this becomes equal to a minus 3 over 3 minus a, or negative of a minus 3, actually, times b minus 4 over negative of b minus 4 times c minus 5 over the negative of c minus 5. This is just negative 1 cubed, which is equal to negative 1. Okay, so that was another simple example that we took right there. And the reason that negative 1 cubed is negative 1 is because negative 1 cycles. So negative 1 squared is just negative 1 times negative 1, which is 1. And 1 times negative 1 is negative 1. Okay, so now let's try another problem, another easy AMC 10-12 problem. So in this problem, what we can do is we can just cross multiply both sides in our first equation to get 3x plus y equal to negative 2x plus 6y. So right now we're just cross multiplying to both sides of the equation. And then what we can do is we can solve the equation. So we can say 5x is just equal to 6y minus y, or 5y, meaning x equal to y. And then we can substitute it into our equation here to get, it will just be x plus 3x, because y is equal to x, divided by 3x minus x, because again, y is equal to x, which means it's equal to 4x by 2x, or 2. Okay, so the main idea for this problem is we just cross multiply, we get x over y, we get what x is in terms of y, and then we plug it into our expression to get what this denominator thing is. And notice that we never actually had to solve for x or y individually. Okay, so now let's try this other problem. And this is a little bit more tricky than the ones we've been doing so far. So I'll give you a minute or two to try and work on this on your own. Okay, so now let me go into the solution for this problem. So the way we can solve this problem is that we can basically have x plus 2 over x equal to y plus 2 over y. So a trick in general for problems is that whenever we have two expressions, we want to put the like expressions together. Because when two expressions are similar, then we can tend to have some nice properties of those expressions. So basically, what we can do here is we can subtract y from both. We can move the y to the other side. So we get x minus y equal to 2 over y minus 2 over x. And this is just by subtracting y from both sides and subtracting minus 2 over x from both sides. And now what? Well, now we can simplify our expression to x minus y equal to 2x minus 2y over xy. And this is just equal to 2 times x minus y over xy. From here, we can cancel out x minus y from both sides because we know x and y are distinct. And if x is not equal to y, then x minus y is not equal to 0. And the reason because when we know they're distinct, and we know x minus y is not 0, then we can divide by x minus y. And then when we divide by x minus y, we get that 1 equal to 2 over xy, or xy equal to 2, which is the answer. And somebody actually brought up a point in the chat when I was reading it. So they said that you can just assume that x is equal to 1, and then you get that xy is equal to 2. And that's a way that you can kind of hack the problem. So if you assume x is 1, then you get that 1 plus 2 equal to y plus 2 over y. And then this means that 3 equal to y plus 2 over y, which means that y is 2. So that could be a way that you can maybe hack the problem. And then from there you can see, okay, x is 1, y is 2, then the product is 2. But the proper solution is just to do something like I showed earlier. But if you don't know how to solve it, then maybe you could hack the problem and kind of assume values to get x and x, y. So that's definitely another way that you can go about it. But again, the key idea here is combining similar terms. So when you combine similar terms, you tend to get nice expressions and properties based on it. Okay, so now let's take a look at our next problem. Well, this is another really interesting and nice problem. So basically we have this expression here and another expression here we want to find. So I'm going to give you some time to try this problem out on yourself. And there's actually a really, really nice idea of how you can actually solve it. So it's a really good solution that you should definitely look at. Okay, so now that you've tried it for a little bit, here's a hint. Let's say that this quantity is a, 49 minus x squared. Let's say this quantity is b. So we have a minus b here is equal to 3. And now let's say this quantity is a again, and this is b. So now you have a plus b here. Does this remind you of anything? A minus b, a plus b. Does that remind you of anything? we go to the solution of this problem. The idea here is you just multiply both of these expressions together. So when you multiply these expressions together, they cancel out by difference of squares. So when you do 49 minus x squared minus square root of 25 minus x squared times square root of 49 minus x squared plus the square root of 25 minus x squared. If you multiply them together, so let me just say that this quantity is equal to, let's just say q, or let's use a better variable. Maybe let's say this quantity is equal to L. Or I'm not sure what a good variable to use. Let's say L. Is this what we want to find, the value? So then when you multiply them together, we get that this first quantity is just 3 we're given. So this is 3. So it's equal to, so when you multiply them out, we can use difference of squares. So this is just going to be equal to square root of 49 minus x squared minus the square root of 25 minus x squared by difference of squares, because this is a minus b, this is a plus b. And then this is equal to 49 minus x squared minus 25 minus x squared equal to 24. But then we know that the first quantity is equal to 3, so we have 3 times the second quantity. And then what is the second quantity? Well, it's L. Let's say it's L. And that's going to be equal to 24. And that means that L, the quantity we want to find, is just equal to 24 divided by 3, or 8. So 8 is your answer for the problem. And that was a really cool trick, because what we do is we multiply them out together. Then now we get something that cancels out really, really nicely, which is definitely great. So that was definitely a really cool trick that we can use. We can now move on to the next type of problems. So this is completing the square. So what is the minimum value of this expression for any real x? So what we can do here is we can find the minimum of the expression. How can we do that? Well, what we can do is we can rewrite it by completing the square, essentially. So basically what we see here is that we have x squared plus 8x. So we know that x plus 4 squared is equal to x squared plus 8x, plus an additional 16 term, right? So then we can rewrite x squared plus 8x plus 16 as, well, we know, plus 8x. We can rewrite this as, well, we know x squared plus, I don't know why I wrote 16. I just said 13, meant 13. So we know x squared plus 8x is equal to x plus 4 squared minus 16. And then we have to add an additional 13 because that's at the end here. We have 13 at the end, so plus 13. The reason I subtracted 16 is because we got an extra 16 term. And this becomes x plus 4 squared minus 3. And how do we find the minimum value of this expression? Well, the minimum value of x plus 4 squared is just 0. And this is just negative 3. So we do 0 minus 3 equal to negative 3 is the overall minimum. Because the minimum of the square of any perfect square is 0. So that's a nice trick that it's really helpful in many cases. And it's great for optimization, finding the minimum or sometimes maximum of quantities. Definitely great to know. Okay, so now let's take a look at our next problem. And this, for those of you familiar with the equation of a circle, you might be familiar with this. So for this problem, the idea here is that we want to find something that satisfies this equation. How can we do that? Well, the idea is we can complete the square, essentially. So we can make it x squared minus 10x. We can group these x terms and group the y terms together. So I'm just moving the 10x and 6y to the other side of the equation. And then we have negative 34 here. So I'm going to complete the square, and we can get x minus 5 squared. It's very similar to this expression here, except x minus 5 squared is just x squared minus 10x plus 25. So we have an additional plus 25. So we have to subtract 25 to account for it. Same thing for the x squared plus 6y term. So we just do y squared y plus 3 squared minus 9. And you know that y squared is just y squared plus 6y plus 9. So you subtract 9 to account for it. And then we get it's equal to negative 34. But then we know that these terms will all cancel. Because negative 25 plus negative 9 is negative 34. So we're left with x minus 5 squared plus y plus 3 squared is equal to 0. And this will only be true when x is equal to 5. And in order for this to be true, we must have both of these terms be 0. Because if you think about it, both of these terms will be 0 or more. So the only way for two of them to actually sum to 0 will have to be, they have to both be equal to 0. Let's just say these are both 0. Because if these are both 0, then we can clearly see that that's the only possibility here. So that's only if these are both equal to 0 can we get the sum of two perfect squares equal to 0. Because the minimum value for a perfect square is 0. And then as you can see here, this will only be true when each of these quantities are 0. The first quantity will be 0 when x is 5. The second one will be 0 when y is negative 3. So the overall sum is just 5 plus negative 3, which is 2. The answer. Okay, so now let's take a look at some factorial problems. So I'll give you a minute or two to try this problem on your own. A hint is to group the factorials and get it that everything's in terms of n factorial only. Okay, so now let's take a look at the solution for this problem. Okay, so this problem, what we're going to do is we're going to factor this into n factorial terms. We're just going to make this n plus 1 times n factorial plus n plus 2 times n plus 1 times n factorial equal to n factorial times 440. So then what we can do is we can rewrite this in terms of n factorial times n plus 1 plus n plus 1 times n plus 2 equal to n factorial times 440. And of course, factorials can't be 0, so we divide out by n factorial to both sides. And then now we can rewrite our left-hand side expression as 1 times n plus 1 plus n plus 2 times n plus 1 equal to 440. And the left-hand side is nothing but n plus 3 times n plus 1. Because we have 1 times n plus 1, n plus 2 times n plus 1. So overall, we have n plus 3 times n plus 1 equal to 440. Okay, so now what can we do from here? Well, one way is just to go on a bash and prime factorize 440 and then just keep writing out all the factors. Keep writing out all the factors of 440. But that would take a long time, and that's a really good chance of making an error. There's actually a much cleverer way of doing this. What we can do is we can see, again, we can rewrite this in terms of n plus 2 plus 1, and then n plus 2 minus 1 equal to 440. This is nothing but n plus 2 squared minus 1 squared by difference of squares. And this is definitely a lot easier than just bashing it out, for sure. It's 440, meaning that n plus 2 squared equal to 441. Because now we know that n plus 2 can either be plus or minus 21. We just take the square root of both sides. So that means either we have n equal to, and of course it cannot be negative because we're given that a positive integer n. And also factorials cannot be negative. So we can just completely eliminate the minus solution. And that means that we have n is 19. The answer. And we're asked to find, oh, that's not the answer actually. We want to find the sum of the digits of n. So it's going to be 1 plus 9 equal to 10. And that was the answer to this problem. So if you have any questions, you can feel free to leave them in the chat. Okay, now let's continue. Here's another factorial problem you can try on your own for some time. So let me just quickly explain the problem. We have this expression, and we want to find out which of the following it is. And we have these 5 option choices you can see here. So somebody asked in the chat, how do you recognize when you need a factoring or algebraic manipulation? Oh, okay. So when do you need a factoring or algebraic manipulation? Generally, it's used in a variety of ways. In fact, many algebra problems are just algebraic manipulation. You manipulate it or you factorize it. So in general, whenever you can group terms together or find similar terms, that can help you factorize it. And generally, whenever you're trying to manipulate something, you're trying to find some quantity in terms of some other quantity, you should be able to see it from there. So it should be clear that when you should use a factoring or algebraic manipulation, and it should just come across you. But in general, a good strategy is to combine like terms in order to factor it. So if you combine, let's say, an x cube and a y cube term, you can use a cube factorization, as we'll learn later in class. Okay, so now let me go into the solution for this problem. The idea here, as many of you have said in the chat, is that what we can do is we can rewrite n plus 2 factorial as n plus 2 times n plus 1 times n factorial minus n plus 1 times n factorial over n factorial. And then we can cancel the n factorial terms because, again, we know it's not 0, to get n plus 2, cancel them out. N plus 2 times n plus 1 minus n plus 1, or minus 1 times n plus 1, which is equal to, well, as you can see here, we have these terms are common. So then you can rewrite this as n plus 2 minus 1 times n plus 1, which is equal to n plus 1 times n plus 1, or n plus 1 squared. And this is a perfect square indeed. So D is the answer for this problem. Okay. Now let's take a look at some functions problem. And this is probably the nicest problem that's covered today. It seems very daunting and intimidating, but it actually is a really nice solution. So let me just go over here. So as you can see here, we have this large function quantity, and this function is equal to this expression, and you want to find the value. So try this problem. this is a really, really nice solution to this seemingly complicated problem. So, definitely. Okay, so some of you are putting some good ideas in the chat. Telescoping is indeed the right solution, as I'll show you later. But knowing that you have to telescoping is only one thing. How do we actually figure out how it telescopes? Yeah, it seems very complicated. So the idea here is we can write let's just get the hang of what this is really. Let's just write what's going on here. What is really going on? So it's just going to be 1 over 2019 squared. So f of 1 over 2019 is just 1 over 2019 squared times 1 minus 1 over 2019 squared. And this is just 2018 over 2019 squared. So I'm just going to rewrite this as 2018 over 2019 squared. That's f of 1 over 2019. What about f of 2 over 2019? Subtract. We're going to subtract f of 2 over 2019, which is just 2 over 2019 squared, times 1 minus 2 over 2019, which is equal to 2017 over 2019 squared. This doesn't seem to be going anywhere. I mean, all we do is really have a ginormous expression. So let's just see what happens at the end. So a good strategy in general is to see telescoping is to write the first few, like rewrite them in terms of an actual expression, the first few and last terms. So the first and last terms, and the first few terms and also the last few terms. And the last terms are just going to be equal to, well, minus, so plus f of 2017 over 2019, which is just 2017 over 2019 squared, times 2 over 2019 squared, minus f of 2018 over 2019, which is just 2018 over 2019 squared, times 1 over 2019 squared. Does it seem familiar? Do these terms seem familiar in any way? They cancel out. Because this is negative and this is positive. So these red terms will cancel out. Same thing with these orange terms. These two terms will also cancel out. Both of them, these terms, will also cancel out. And overall, as you can see here, we have a total of 2018 terms. Basically, we have 2018 terms. The first one will cancel with the last one. The second one will cancel with the second to last one, so on. We'll keep canceling all of them. And we'll just be left with 0. Because all the pairs of terms, first and last term cancel. Second and second last term cancel. All of them cancel. And we're left with just 0. And that is the solution here. Because when we're canceling these terms. So again, the reason that this does work is because the reason that how do you actually think of like just writing these out and seeing telescoping? So in general, when you have a long expression, writing the first few, writing the last few terms, they can help you get a feel for what is going on here. They can help you get a feel of what the problem is doing and what are their patterns in the terms. Okay, so now we're going to look at some cubic factorizations. The first one, very important factorization. X plus y cubed is x cubed plus y cubed plus 3xy times x plus y. This is what you should definitely memorize. Or if you don't memorize it, it's okay. You can always rederive it later, but this is something that it's really good to know and memorize. This next expression is just another way of rewriting the first expression. Again, you don't have to memorize this expression, but it's just still good to know that these are ways of expressing it. But in general, this expression is more important to know because it can help us manipulate x plus y cubed. Next, we have x minus y cubed. It's going to be equal to x cubed minus 3xy times x minus y plus y cubed. So then what we can see here is that we have another way of rewriting it as we have another way of rewriting it. This one you should definitely memorize. The second one, there's no need to memorize it, but it's still good to know. And it's okay if you don't memorize it right now. I'm not expecting you all to memorize it right now, but it's still good to know, and you can always rewrite it. So it's not that important to memorize it, but I still highly encourage it. But the second way of writing it is not needed necessarily. It's just another way of expressing it that can be good to know at times. And we also have that x cubed minus y cubed is equal to x minus y times x squared plus xy plus y squared. So as you can see here, this is another important factorization. And this is something that people, including I, also used to get confused with earlier. So basically when we do x cubed minus y cubed, basically we have this term should also be negative, and then this term should be positive here. So basically, when you're doing factorizing x minus y cubed, the x minus y term, this sign has to be negative, and this sign has to be positive. But when you're doing x cubed plus y cubed, this sign has to be positive, and this sign has to be negative. So you can always remember that one is plus, one is minus, and the other is minus, and the other is plus. And something that people get confused with is they think that both are plus, but generally memorize that one is plus. Remember that one is plus and one is minus. So they're opposite. And for x cubed plus y cubed, the first x plus y is plus, and the second is minus. And for the x minus y cubed, first is minus, second is plus. This last expression here, another seemingly complicated expression. Basically, we have that x plus y plus z cubed minus 3xyz is equal to x plus y plus z times x squared plus y squared plus z squared minus xy minus xz minus yz. Yes, it is long, but it can be useful at times. And don't worry if you don't remember now. It'll always be there. There will be a handout sent out at the end of this class, which will contain all the important formulas for the AMC10, including this one. Okay, so now let's take a look at these types of problems where if we have x plus 1 over x equal to some quantity, to find expressions in terms of them. So what we can do here is that x squared plus 1 over x squared, how do we find that in terms of x plus 1 over x? One way, the hard way, is just to directly find the value of x. But that will be hard, and squaring it and then 1 divided by that doesn't take too much effort. Okay, so how can we find x squared plus 1 over x squared? Oh, sorry. Looks like there's a typo here. This should be x minus y cubed. So that's a small typo. Sorry about that. Oh no, this would be x plus y. Oops, looks like I turned off the sound. So now let me just repeat what I said. So we have x plus 1 over x is equal to 3. And we have x plus 1 over x squared is going to be, we can square it out, because whenever we're trying to find x squared plus 1 over x squared, we just square the expression, and we get that that's equal to x squared plus x times 1 over x plus x times 1 over x plus 1 over x squared. So we're just squaring this expression so we can try to get these terms here. And this is equal to x squared plus 1, because these cancel, plus 1 again, because these cancel, plus 1 over x squared, which is equal to x squared plus 1 over x squared plus 2. Okay, so now we know that 3 squared, because x plus 1 over x is 3, is equal to x squared plus 1 over x squared plus 2. Meaning that 9 equal to, this is just 9. And that means that x squared plus 1 over x squared is just 7. So this is 7. Now what about x cubed plus 1 over x cubed? How can we do that? Well, in order to do that, how can we do that? Well, we can just do x cubed plus 1 over x cubed. Well, what we can think about doing here is saying that, let's say that y equals 1 over x. So then this can be written as x cubed plus 1 over x cubed, which is equal to x cubed plus y cubed. And what do we know the value of this is? The value of this is equal to x plus y cubed. So then this is equal to x plus y times x squared minus xy plus y squared by the sum of cubes formula. Remember we learned on the previous page that x cubed plus y cubed is equal to x plus y times x squared minus xy plus y squared. Okay, so as you can see here, now what do we do? Well, now what we can do from here is that we can see that these are expressions we want. So we know that x plus y. Let's substitute y as 1 over x again. The only reason I made the substitution of y is to make it clear that we're using the sum of cubes formula. So I'll just say that we can substitute y as 1 over x. And y is just 1 over x. So then this middle term is just going to be minus x times 1 over x. So it's going to be minus x times 1 over x, which is just going to be equal to 1. So minus 1. Plus y squared would just be 1 over x squared. So plus 1 over x squared. And then from here, we know that x plus 1 over x is just 3, right? We found it's 3. So 3 times, and we know that x squared minus 1 over x squared. So we know that x squared plus 1 over x squared is 7. So this is going to be times 7 minus 1 is equal to 3 times 6, or 18. So this will be 18. Okay, so now let's look at x to the 4th plus 1 over x to the 4th. How can we find that out? Well, what we can do is you can just see that x squared plus 1 over x squared squared, if we square this expression, we get x to the 4th plus x squared times 1 over x squared plus 1 over x squared times x squared plus 1 over x to the 4th. We're just expanding it out here. And we know that this is 1, and this is 1. So this simplifies to x to the 4th plus 1 over x to the 4th plus 2. And if x squared plus 1 over x squared is 7, then we have that 7 squared is equal to x to the 4th plus 1 over x to the 4th plus 2. So this means 49 is x to the 4th plus 1 over x to the 4th plus 2, or that x to the 4th plus 1 over x to the 4th is 47. So that's our answer to this part. So 18, 47, and 7. 7, 18, and 47 are our 3 answers. So in general, if x plus 1 over x is equal to k, so let's say make any variable k, then x squared plus 1 over x squared is just going to be equal to k squared minus 2. X cubed plus 1 over x cubed will be just equal to k cubed minus 3k. And in general, x to the 4th plus 1 over x to the 4th will just be equal to k squared minus 2 squared minus 2. And you can easily derive them from the same process we took to calculate these. I won't show that there because of time, but this is definitely a very useful thing that you should keep in handy. Okay, so now we're going to be doing raffles. So this week we're going to be raffling an art problem solving gift certificate and a Wolfram notebook subscription. And the Wolfram notebook subscription will be raffled amongst everyone, but the art of problem solving gift certificate will be raffled only amongst the people who attempt the homework problems from this week. So this is just to encourage people to attempt the homework. And by attempting the homework, you don't have to solve many of the problems, or you don't even have to solve one of the problems. You just have to attempt the problems, and you can post your thoughts and solutions in the comments of this video. So overall, that should give you overall. So you should at least attempt the problems, and then you'll be entered into a raffle for art or problem solving gift certificate, which is a $25 value. So the Wolfram notebook will be raffled amongst everyone, and the art or problem solving gift certificate will be raffled only amongst the people who attempt the homework. And you don't have to, you don't have to solve even one of the problems. You just have to attempt them and post your ideas, thoughts, or solutions. You just basically have to post your solutions for some problems or thoughts or ideas. Okay, so while you're waiting, you can try this problem. It's actually a really interesting problem, and there's multiple ways to solve the problem. You should post your solutions after the class is over, so you can try the homework problems after. And this has a really clever trick. And a hint for those of you working on it is to combine similar terms, combine similar expressions, and see how you can manipulate them and use some factorizations that we learned. So for those of you working on this problem, there's a really neat trick to combining them and using some nice factorizations. So Okay, so now that you've had a chance to try this problem or take a break, now let's resume. Okay, so how can we actually evaluate this expression? Well, what we can do is we can actually do something really clever here. So one person said in the chat, I was looking at it, that you can combine these terms to get x to the fifth plus y to the fifth over x squared y squared. And that does definitely work. And this does lead to a valid solution, except there's an easier way of going about this. There's an easier way to solve this problem. And like at the hint I said, combining similar expressions, creating similar expressions, and then factorizing them together. So that was the hint I gave earlier. And what we can do here is we can make this into x cubed divided by x squared plus x cubed divided by y squared plus y cubed divided by x squared plus y cubed divided by y squared. Okay, so what we notice here is that these terms and these terms look a lot like, are very similar, right? Same thing for these two terms. They look very similar. So the idea here is that we can rewrite this as x cubed plus y cubed over x squared plus x cubed plus y cubed over y squared. Okay, so that's interesting. Now we see that x cubed plus y cubed, that shows up yet again. How can we find the value of x cubed plus y cubed? Well, we can use our factorization tricks that we learned. So we can know that x cubed plus y cubed equal to x plus y, so x plus y, times x squared minus xy plus y squared, which is equal to 4 times x squared minus xy plus y squared, which is going to be equal to, well, x squared, x plus y squared, minus 3xy. So as you can see here, we have that x squared minus xy plus y squared. So x plus y squared is just x squared plus 2xy plus y squared. And then we subtract 3xy to get x squared minus xy plus y squared. This is equal to 4 times x plus y squared. Well, we know x plus y is just 4 squared. So we do 4 squared minus 3xy. So minus 3 times negative 2, which is equal to 4 times 16 plus 6, equal to 4 times 22, or 88, the answer. So 88 is the answer for this problem. Yeah, okay. So that was a really nice problem. The idea is when you convert everything to similar expressions, we can combine them and then we can factorize them. So that's the general trick you want to keep in mind when you're dealing with these types of factorization and algebraic manipulation problems. Sorry about that. Actually, it's not 88. 88 is not the final answer for this problem. 88 is just the value of x cubed plus y cubed. So 88 is not the answer. Sorry, I forgot that we have to actually evaluate x cubed plus y cubed, 88 divided by x squared, plus 88 divided by y squared. So I completely missed that even though we found x cubed plus y cubed, we're not done with the problem yet. We only found an intermediate step. So it's actually going to be equal to 88 y squared plus 88 x squared over x squared y squared, which is equal to 88 times x squared y squared over xy squared. So it's going to be xy squared. So negative 2 squared, which is equal to 88 times x squared plus y squared over 4, which is equal to 22 times x squared plus y squared. Because now how can we find x squared plus y squared? Well, x squared plus y squared is just equal to x plus y squared. So x plus y squared minus 2xy equal to 4 squared minus 2 times negative 2, which is equal to 4 squared plus 4, or 20. So the answer is just going to be 22 times 20, which is 440, not 88. Okay, so that's it for this problem. And this problem was really clever because we combine these like expressions together. Okay, now let's take a look at this problem from Amy. And even though it's from Amy, it actually is a really, really nice solution. So it's, even though it's a somewhat tricky problem, it seems as if it has a really nice and elegant solution. So definitely stick around for that. And somebody actually predicted in the chat earlier that there's going to be a problem using polynomials and algebraic manipulation. And that is correct. This is the problem using polynomials and algebraic manipulation. Okay, so now that you've had some time to try it out, I'm going to show you a really nice solution to this problem. So this solution is going to seem it's going to seem extremely nice. So let me just explain it. So we have this polynomial. So what we notice here is that r plus s plus t equal to 0. Because the x squared, we can rewrite this as 8x cubed plus 0x squared plus 1001x plus 2008. So the sum of the roots is just going to be equal to 0 divided by 8, or just 0. Negative 0 divided by 8, or 0. And then what we do here, since we know r plus s plus t is 0, then that means r plus s cubed plus s plus t cubed plus t plus r cubed is just going to be equal to negative t cubed, because we know that r plus s is equal to 0 minus t, or negative t. And we know that r plus t is equal to 0 minus s, or negative s. And same thing for s plus t is negative r. And that means that we have minus t cubed plus minus r cubed plus minus s cubed, which is equal to negative 1 cubed times t cubed plus negative 1 cubed times r cubed plus negative 1 cubed times s cubed, which is just going to be equal to, well, negative 1 cubed is negative 1, because negative 1 squared is 1, and 1 times negative 1 is negative 1, and then t cubed, so negative 1 times t cubed plus r cubed plus s cubed. Okay, so now we need to find the negative of r cubed plus s cubed plus t cubed. How can we do that? Well, we can use a very clever factorization here. We know that r cubed plus s cubed plus t cubed minus 3rst equal to r plus s plus t times r squared plus s squared plus t squared minus rs minus rt minus st. So this is a factorization that we learned about earlier. So let me just scroll back just to show you. It was this factorization right here. But this time I'm just using r, s, and t instead of x, y, and z. Okay, so now what? Well, we know that r plus s plus t is 0. So if r plus s plus t is 0, then this is just 0, right? We found r plus t is 0. And this whole thing becomes 0. This is just equal to 0. So you have r cubed plus s cubed plus t cubed minus 3RST is just 0, because 0 times anything is 0. So that means we have r cubed plus s cubed plus t cubed is 3RST. Okay, so now we know what r cubed plus s cubed plus c cubed is. Just 3RST. And what is RST? Well, by Vieta's formula, RST is just equal to, well, negative, positive, negative. So negative, negative, positive, negative. Oh, this underline looks confusing, so I'm just going to erase that. Negative, positive, negative. So RST is equal to negative 2008 divided by 8 equal to negative 126. So we can substitute that in to our expression. And from there, we can see that this expression is just going to be equal to, we can plug that in to get r cubed plus s cubed plus t cubed is just equal to 3 times RST. And we know that RST is just equal to, negative 2008 divided by 8. So that means we know that r cubed plus s cubed plus t cubed is just going to be equal to, r cubed plus s cubed plus t cubed will just be equal to 3 times RST, as you can see here. And what is RST? Negative 126. So that from here, you can easily figure out that r cubed plus s cubed plus t cubed will just be, oh, this is not negative 126, this is negative 251. So it's going to be equal to negative 3 times negative 251, which is negative 753. So that means we know r cubed, we know this expression, r cubed plus s cubed plus t cubed is negative 753, meaning r cubed plus s cubed plus t cubed is just, or this expression here is just going to be equal to negative of negative 753, or 753. The answer, so we know 753 is the answer. Okay, so now let's take a look at our next problem. So now we're going to look at Simon's favorite factoring trick. So by Simon's favorite factoring trick, we know that x plus y plus xy is 80. We want to find the value of x. So from here, what we can do is we can rewrite the Simon's favorite factoring trick as, so by Simon's favorite factoring trick, we know that we have some terms here. We want to get x, y, and xy terms. So in general, Simon's favorite factoring trick is always useful whenever you have xy terms, x terms, and y terms. So Simon's favorite factoring trick gives us a nice way of combining all of them and making it easy for us. So what we can do here is let's just put x and y. Oops, I don't know why I erased that. X and y here. We can see that we can add 1 and add 1 here, because somehow we need to get an x term, and somehow we also need to get a y term. So if you do plus 1 here, now we get an xy term, and we also get a y term from multiplying these two expressions. But then we also need to get an x term. So we can just multiply this plus 1 here, because then we have an 1 times x equal to x term. But then this also has an additional 1 term, 1 times 1. So if we expand this out, we get xy plus x plus y plus 1. So we have an extra 1. So then we need to subtract 1 to account for it. So that means we have that x plus 1 times y plus 1 minus 1 equal to 80. And that means that x plus 1 times y plus 1 equal to 81. Okay, so now what? Well, now we can just look at the different possible factors. So the different factors are either 181, 327, 9 and 9, 27 and 3, 81 and 1. So these are the possible factors. Except we know that x is greater than y. So these three cases all don't work. Because in these first three cases that are crossed out, y is always going to be either equal to x or less than x, or greater than x. But only in these two cases do we actually have x greater than y. Because 27 is greater than 3, 81 is greater than 1. But except, in this first case, we get that x is 26 and y is 2. In the second case, we get x is 80 and y is 0. Because we always know that this is 1 is y plus 1, and 81 is x plus 1. So then we know that x has to be 80 and y has to be 0. Okay, so now as you can see here, this second case does not work because y has to be greater than 0. So y cannot be equal to 0. So we're left with the only possible solution, 26, 2. So the answer should be 26. Okay, so we don't have enough time, so I'm going to skip this problem for now. It will probably end up in your homework problems for this class. So you can try this problem as it will be part of the homework problems, and there should be a separate solution video. So now let's look at this problem from the AME. And again, even though it's an AME problem, it actually has a really good solution. So the idea here is, let's say a is x squared and b is y squared. Okay, so now we know that a is x squared and b is y squared. So as you can see here, we can rewrite this as b plus 3ab equal to 30a plus 517. And from here, what we can do is we can rewrite this as 3ab plus b minus 30a equal to 517. Then we can divide by 3 to both sides, to the whole sides, to get ab plus b over 3 minus 10a equal to 517 by 3. This looks a lot like Simon's favorite fraction trick, because we have an ab term, and we also have b and a terms. So by Simon's favorite factoring trick, we can rewrite this as a plus 1/3. We have, let me write it this way. So we have a times something times b times something, right? To get an ab term. We also need a b divided by 3 term. So in order to get a b divided by 3 term, let's do plus 1/3 here. Because then when we multiply 1/3 by b, we get b divided by 3. But we also need a minus 10a term. So let's do minus 10 here, because then we do minus 10 times a. But then, as you can see here, we have an extra, let's use yellow. We have an extra 1/3 times negative 10, or extra negative 10/3 term. So we add back 10/3 equal to 517 by 3. And then from here, what we can do is we can subtract 10/3 from both sides to get a plus 1/3 times b minus 10 equal to 507 by 3. And now what? Well, firstly, we need these x and y to be integers. And if x and y are integers, so are a and b. So we need a and b to be integers. So then from here, let's just multiply by the whole equation by 3. Again, to get 3a plus 1 times b minus 10. Right, because we multiply this by 3 to get 3 times a plus 3 times 1/3, or 1, is 507 by 3, or 507 when we multiply by 3. And now let's look at the different possible factors. So the different possible factors are going to be 1, 507, or let's just use a different color to make it clear. Let's say it's 1 and 507, 3 and 169, 13 and 39, 39 and 13, 169 and 3, and 507 and 1. So these are the different possibilities, right? Okay, so firstly, we know that it has to be of the form 3a plus 1. So that means a, then each of these terms has to leave a remainder of 1 when let's substitute back, just to make it a little bit more clear now. So let's say 3x squared and 3y squared minus 10. Because again, we just made these substitutions in the beginning. So 3x squared plus 1 times y squared minus 10. So firstly, we can see that the only possibilities for 3x squared plus 1 are those numbers that leave a remainder of 1 when divided by 3. So 1 leaves a remainder of 1 when divided by 3, right? 1 leaves a remainder of 1 when divided by 3. 3 does not leave a remainder of 1 when divided by 3, because only numbers of the form 3x squared plus 1. So they have to leave a remainder of 1 when divided by 3. 13 works too, because 13 leaves a remainder of 1 when divided by 3. 39 does not work, because it leaves a remainder of 0 when divided by 3. 169 does work, and 507 doesn't work because it's multiple of 3. So now we've eliminated some possibilities. So in this first possibility, we have that 3x squared plus 1 is 1, meaning that 3x squared plus 1 is 1, or 3x squared is 0. And that means that x squared is 0, or x equal to 0. Okay, so x is 0, that doesn't work, because or it can work, never mind. And maybe it does work. But then here, from y, we see that if y squared minus 10 is 507, y squared is just equal to 517. So then this doesn't work, because y has to be an integer. And no integer squared can be 517, since the square root of 517 is not an integer. So this case does not work, so I'm just going to cross that out. In the second case here, we have that, we already know the second case doesn't work, because we eliminated it in the beginning, because 3 does not leave a remainder of 1 when divided by 3. The third case, 13 and 39, well, for that case, let me just cross these out really quickly. For the 13 and 39 case, we can see that if 3x squared plus 1 is 13, 3x squared will have to be equal to 12, or x squared will have to be equal to 4. And that means x is plus or minus 2. And we'll see later that it shouldn't matter whether x is positive or negative. And the final case is 169 and 3 that we have to check. Oh, and also, I forgot to mention, this is 3y squared. 3x squared plus 1 is 13. And then we also have that y squared minus 10 has to equal to 39, meaning that y squared will be 49, or y will be plus or minus 7. Okay, so that's the, and this does seem to work, since we have the we get x and y integer values. So this does seem to work. Let's check this second to last case here, 169 and 3. So in this case here, we have 3x squared plus 1 is 169, or 3x squared is 168, or x squared is 56. But this again doesn't work, because no perfect square is equal to 56. 56 is not a perfect square, so no integer squared can be 56. Okay, so now what? Well, if no perfect square can be 56, now what can we do? Well, now clearly the only solution is 13 and 39. But then what about plus or minus? We don't know the exact values of x and y. But we don't need to know the exact values of x and y. We just have to find 3x squared y squared. So then it's just going to be 3 times plus or minus 2 squared, which is 4 times 49. And see, it doesn't matter whether it was plus or minus, because 2 squared is 4, negative 2 squared is also 4. Same thing for 7. 7 squared is 49, and negative 7 squared is also 49. So it doesn't matter what we choose, but it's just going to be equal to 3 times 4 times 49, which is 196. And this is just equal to 588. Okay, so now let's take a look at the Sophie Germain's identity problems using that. Okay, so as you can see here, we have Sophie Germain's identity. It says that x to the fourth plus 4 times y to the fourth is equal to x squared minus 2xy plus 2y squared times x squared plus 2xy plus 2y squared. Okay, so we're actually going to use this to simplify this problem drastically. Okay, so this seems quite out of place. Like, how are we using any factorization here? But there's a really nice trick to doing this one. So the idea here is whenever we have large exponents, it's hard to deal with. 2 to the 202, that's 202. There's nothing we can really want to use there. And then, as you can see here, we don't really know what to use there. But we can look at this next expression here. Large exponents, that's very hard to deal with. Let's just say that we have a variable x, or y. Let's say y is equal to 2 to the 50. So let's say y equals 2 to the 50. That means that 2 times y to the fourth, 2 to the 202 plus 202 is just going to be equal to 2 squared times 2 to the 100, which is equal to 2 squared times 2 to the 50 to the 4. That's just 4 times y to the 4. plus 202 again, right? So this is our expression in terms of y. And the second expression in terms of y is just 2 to the 101 plus 2 to the 51 plus 1 will just be equal to 2 to the 1 times 2 to the 50 squared equal to 2 times y squared. Or then we also have to add 2 to the 51 and then also plus 2 to the 1 times 2 to the 50 plus 1, which is equal to 2 times x y squared plus 2 times y plus 1. Right? Okay, so now we need to divide 4 to the y to the 4th divided by this. So how can we do that? Well, this is very interesting here. So do you see a connection? So I'm just going to rewrite this actually. This is also, I'm just going to rewrite this as 1 plus 2y squared plus, I'm just rewriting it in a way to make it seem easier for you to see. Does this expression seem familiar to this expression here? Does it seem familiar? Yes, because what we can do here is we can just use Sophie Germain's identity to get that when you do 1 plus 2y plus 2y squared times 1 minus 2y plus 2y squared will just be equal to, by Sophie Germain's identity, 1 to the 4th plus 4 times y to the 4th. And, oh, I should probably make that a little bit more clear. That might have been confusing for some of you to follow. So let's just say that x is equal to 1. Then this will just be equal to x plus 2y, or 2 times x times y, plus 2y squared. X squared plus 2y, it's just going to be 1 squared. So x squared plus 2xy plus 2y squared times x squared minus 2xy, since x is 1 anyways, plus 2y squared. And this is just by Sophie Germain's identity equal to x to the 4 minus 4 times y to the 4 plus 4 times y to the 4 from the problem here. And now what can we do is we can actually simplify this expression in terms of x to get 1 plus 4 times y to the 4, and this to the power of 4 just disappears because 1 to the 4 is 1. And now what we can do from here is we can see that if 4y to the 4 plus 1 is equal to this expression, then when you divide this quantity here, 4y to the 4 plus 202 by this expression, well, clearly we can see that when we divide 4y to the 4 plus 202, when you divide that by 1 plus 2y plus 2y squared, it's equal to, well, we know that 4y to the 4th plus 1 evenly divides 1 plus 2y plus 2y squared by Sophie Germain's identity. So this is an integer. But then we also know we're adding 201 divided by 1 plus 2y plus 2y squared. So then we also know that this will be an integer. And this will obviously leave a remainder of 201. So we leave a remainder of 201 when divided by that. So 201 is the answer. 201. And we can clearly see that 201 is less than 2 to the 101 times 2 to the 51 plus 1. So the remainder is, we cannot reduce the remainder anymore. So 201 is indeed the remainder. Because, or let's actually, let me explain a better way of rewriting it. Let's just say that this is equal to 4y to the 4th plus 201. And we know that 4y to the 4th plus 201 is evenly divisible by this quantity here. So then we can just rewrite that, see that 201 is the remainder. And that's the answer for this problem. Okay, so it looks like we're just out of time here. And this problem might be in your homework. It was a tricky problem, but we did not have time to go over it. This problem should be in your homework for this week's. So thank you all for coming to today's class. I hope you found some useful and learned something new. And somebody actually asked in a question, what is the motivation for using Sophie Germain's on this problem? The motivation is, first, we just rewrite it in terms of variables. But then we see that this expression here looks so similar to an expression we know here as Sophie Germain. The two highlighted portions I explained earlier is so similar. So that's why we considered using Sophie Germain's, because these expressions are so similar that we see that, oh, there's something here that's so similar. So, and also we also have that other term here. Let me also show that this term here also is of the form something to the fourth plus something to the fourth. So whenever you have to the fourth powers, we also can use Sophie Germain's there. So that was the motivation behind the solution. So thank you for coming to this class. Hope to see you all next time. And please make sure to try the practice problems from this week and share your